amplifier. So till now we discussed about the MOSFET region of operation, why we are going for a saturation region, why we are talking about the linear region. These all are the basics stuff. And then we discuss about the CMOS inverter. In a CMOS inverter, we discuss okay how the MOSFET in different region on the basis of the input is changing. Okay, that MOSFET is start from the cutoff with the for NMOS and PMOS start with the linear, and now it is changing that, and the point at which that both MOSFET in saturation region, that is called a trip point. At that point that you will find the large of current, and this point that both MOSFET in saturation region, and it will provide a high power dissipation. So this is the part of CMOS inverter. Now I am going to start an amplifier. So what is that meaning of that? So basically I am just explaining in such a way. Okay, you have a one box and we have one input, we have one output, and we have a one common. I am providing the input with respect of something, let this with respect of this, and we are trying to determine the output voltage with respect of this node. Let I am providing the input voltage is like this, and we are trying to determine in such a way that it will be an amplifier. Is it? So I am providing a small input voltage and finding that the large amount of change at the output side, that is called amplifier. Here I am using a device that is called MOSFET. We are using a MOSFET. Okay. So for making that this MOSFET in an amplifier, you must understand that MOSFET must be in saturation region. Whenever you are talking about the MOSFET as an amplifier, that always MOSFET work as a saturation region. Whenever you think about the MOSFET behave like a resistor, you use a MOSFET as a linear region. And if you talk at the MOSFET work as a saturation region, as an amplifier, you must that it must be in saturation region. What is the benefit when it is in a saturation region? I am just explaining in a curve. Okay, you can understand everything with the curve only. Let this is ID versus VGS graph, and you are changing that VGS, you find that current is like this. So this is the threshold voltage of the MOSFET. Let this is NMOS. After that it will be enter in a saturation region, and then it will be a linear region. This is the region when after that it will be in linear, and this is the region before that it will be in cutoff, and in between it is saturation region. So if you are looking it at here, and if you are providing that a small change, let you are setting that voltage, let you are provide that gate voltage is Vx, and you are changing a small delta Vx at this point. Let you are changing a delta Vx here. So what will be the changing at the output? The output is changing like this, and it is changing here. So a small change in the input voltage, you find the large amount of change in the current. That is the representation of transconductance, that is called GM. GM is equal to what? That slope is what? That GM is called as dou ID by dou VGS. Okay. And that will be help in your amplification for the gain. And if you are looking this point, that if you are changing a small voltage in small input voltage, you find the large amount of change on the current, that is dou ID by dou VGS is large in a saturation region. But if you talk about a linear region, that transconductance is not higher as compared to saturation region. The saturation region will provide the higher transconductance. So that's why we always think like this, that whenever you are talking about the MOSFET for an amplifier, that MOSFET must be in saturation. It may be in common source, it may be in current mirror, it will be in and OTA, differential amplifier, everywhere we are thinking that MOSFET must be in saturation because I am using the MOSFET as an amplifier. Okay, so this is the very basic understanding. Okay, you are designing, okay, you are using this box where you are providing the input voltage and you are trying to find out output voltage, where that one node has behaved like an input with respect of some common mode and one output is taken with respect of common. So this common is called common source. We have a different like we in the MOSFET we have a source, drain and gate. So it may be a common source, it may be a common drain, it may be a common gate. I am starting with a common source amplifier, and that is very important topic for an amplifier. So common source amplifier means what? That we are using one MOSFET. Let this is gate, this is drain and this is source. So here on the gate side you are providing the voltage with respect of source, that source is common, so the gate voltage with respect of source voltage, and that you are checking that output at the drain with respect of source. So that common node is source, that's why it is called common source. Whenever you talk about the common drain, you are providing the input at the gate and you are taking the output of the source, that is called common drain. When you are talking about the common gate, you are providing that input at the source and you are taking the output at the drain. So whenever you are saying that common node terminal, that where would be that with respect of this the input is providing and with respect of that you are talking about the output. This is called common. Okay, that is a common source. Okay, so let's talk about common source amplifier with a resistive load. So that is very basic circuit. Common source amplifier with resistive load. So I have a MOSFET and I am using as a load as a resistance, that is RD, that drain resistance, that RD, and you can say that R. Here you have a VDD, you have a gate at here, you have a drain at here, you have a source at here, and this source is a that grounded. So I am using a gate to source voltage like this, and I am trying to determine the output voltage at the drain with respect of source node, that is source is grounded. Okay, so this is your common source amplifier with a resistive load. Okay, so whenever I am saying that common source amplifier, firstly you make a circuit in such a way that source is common and you are providing the input at the gate and you are talking about the output at the drain, and you must set that MOSFET in a saturation region. Whenever you are talking about that amplifier, you firstly set the operating point. The operating point at which that MOSFET is work as in a saturation region. You provide the gate to source voltage and you are trying to determine what is the VDS, where that VDS should be greater than VGS minus VTS, then only the MOSFET in saturation region. So firstly you will check it the MOSFET in saturation region or not, and then you make a small signal model. After that you are making the small signal model where it is just a small signal model is called as a change. Okay, whenever you have a change of voltage, you are taking that as the small signal, and whenever you are finding that is a constant, it will be 0. So a small signal will always represent the derivative of that signal. Okay, so it will be the derivative of that MOSFET, that is called small signal model. And third, you will find the gain of that, or that you are finding the Z in, the input impedance, the output impedance. Yes. So this is the way you can proceed for an amplifier. So firstly, I will check that operating point. Okay. The MOSFET must be in saturation region. Okay. So just understand in such a way कि okay, you have a resistance here and you have MOSFET and you are providing the input here with respect of source that is grounded, and you have a RD and you have a V out, and this is VDD. So if the input voltage is changes, that as per the input voltage is change or increases, your ID current, your drain current is increases. The drain current towards the MOSFET will be increases. And what will be happen at this node? V out is equal to VDD minus ID RD. So basically, as per that input voltage is changes, your output is decreasing. Why? Because RD is fixed, VDD is fixed, but ID is changes with respect of input voltage. Just think in such a way, okay, you have a input voltage, or that is called gate voltage, and you have a ID, and you are talking about as per the input voltage is changes, your current is like this and this. Is it okay? So this is an after VT at the MOSFET in saturation region, and then it will be a linear region. Okay, if you talk about what is the drain voltage, or you are saying that output voltage, because the drain voltage is your output voltage. What will be the output voltage? The output voltage when the input is 0, or before that VTS, let the MOSFET is ideal. Before that VTS, the ID is nearly about 0. If practical, it is nanoampere or picoampere. That current is very small. So when the input voltage is less than VTH, that output current, the drain current is nearly about 0. So what is V out? V out is VDD. V out is VDD when the input voltage is less than VTH. So I can say that this will be near about like this. Yes, is it okay? So this is V out is equal to VDD minus IDRD when the input voltage is lesser than the threshold voltage. So V out is near about VDD where the ID is very small. And but when you are talking about when the input voltage increases after that VTH, your current is increasing exponentially or square term, and then it will be a linear after that when the MOSFET in a linear region. But after that VTH, the MOSFET in saturation, your output voltage is also decreases because your ID is increases after that when the input voltage is greater than threshold voltage, and your V out is not VDD, it is VDD minus IDRD. And if this voltage is greater than VGS minus VTH, then it will be in saturation region. Okay, so for that output, the drain voltage is greater than VGS minus overdrive voltage. Okay, so that MOSFET output voltage is decreasing like this, and at this point where that MOSFET enters in a linear region, it will be here as V out is decreases with respect of VDD minus IDRD, where ID is a linear current. So this is the voltage where that V out is VGS minus VTH. Whenever that V out is greater than VGS minus VTH, that the output is MOSFET in saturation region, and V out is decreases with that VDD minus IDRD. And when Vout voltage is less than VGS minus VTH, your MOSFET is in a linear region and it is decreases like this. So I am just focusing on the saturation region. I am not interested on the linear region. I am just interested in saturation. I am not interested in cutoff and linear. I am only focused on that region where the MOSFET in saturation region. And let I am assuming okay, you have this voltage that is Vx voltage. I am just operating that the operating voltage. I am just using the MOSFET voltage is let Vx. This is Vx voltage, and if you are changing that Vx with the delta Vx on the right and left, a small change in here, that you will find the large change and the output current like this. So I am just interested to determine that okay, if you have a Vx is changes, that current is changes like this. Similarly, if we are changing that Vx, you have this amount of change and the Vout. That Vout is changing at here, that is changing like this. Yes, everyone understand or not? I am just explaining in such a way that your Vout is also changing. Why? Because Vout is VDD minus IDRD. ID is increases, Vout is VDD minus IDRD. That ID will increase, though Vout will decreases. But if I am talking about, let I am putting that this gate voltage, let I am putting that the gate voltage is Vx. Let make it 0.5 volt. Okay, I am just talking about let this is 0.5 volt, and you are changing a plus minus some millivolt. Let you are changing that 10 millivolt. If you are changing in a 500 millivolt, that change of 510 to 490. So you are changing the voltage of 510 to 490. This is 510 and this is 490 millivolt. 590 millivolt to 490 millivolt, you are changing here. Your output voltage or your that current is changing a large amount of that. Why? Because the MOSFET in a saturation region there. So I can say that okay, that if you are providing the 0.5 volt with a 10 plus minus 10 millivolt changes, your output is changing like VDD minus IDRD, and that will also change a large amount. Is it okay? So that's why it is a small change on the input voltage, you are finding the large change on the output side, and large change on the current, output current, that a drain current, where that you will find that high transconductance. So the main point is, what is Vx? How can you determine the Vx? Okay, that major point at here, that if we are putting a particular value of that Vx, so that your Vx should be in such a way, if you are changing a delta X, that MOSFET should be in saturation region. Let you are taking that this is a Vx. If you are putting this is a Vx, let you are taking as a Vx at here. So what is happening? If you are changing a delta Vx, it may be entering a linear region. So at the boundary of that, it will be a problem. If you are putting that Vx at here, if you are assuming that Vx at here, if you are taking that delta Vx, so it may be the MOSFET enter in a cutoff region. So MOSFET must be in a saturation region in such a way that if you are changing a small amount of delta Vx, it maintains the saturation region, and that region is such a way that MOSFET maintains saturation region and it will amplify a good amount of output voltage. If you are choosing a corner of that, it will be effect that MOSFET enter in a cutoff or MOSFET enter in a linear region. Is it okay? So it will not provide a good amplification. It may be cut a bottom or upside. If you are providing a particular good voltage at the operating voltage at the gate side, it will provide a good amount of amplification. So basically I am just explaining in such a way that you are changing the input voltage. So the input voltage is changes the current, and this current will changes your output, because the output is changes, Vout is dependent on VDD minus IDRD. So when the MOSFET is off, the output voltage is VDD. When the MOSFET in saturation, the output is changes with respect of ID. And when the MOSFET in linear, the output is changes with respect of ID. But at saturation region that have a large amount of change, if you talk about linear or cutoff, there is not changes of the Vout as much. So the point at which you are focusing that what will be the operating point. Your operating point should be very good. Okay, if you have operating point is good, then only it will be in good region of the MOSFET. Okay, so let's talk about that operating point. So I am just making that circuit like this. Okay, let this is Vout, and this is your VDD, and this is your RD. And we know that Vout can be changes from VDD to 0. Okay, Vout can be changes from 0 to VDD. So if this is happening, so what will be present? Just please understand here, I am just explaining the operating point in a curvature form. Okay, you have a ID and you have a Vout, that is called VDS. Okay, I am making that circuit in such a way that you have a input voltage, you have a source, and now you have Vout. I am just breaking that circuit, that the bottom part at here and the upper part is here. I am just changing that Vout. If Vout is changing, what will be that curve of that? And if Vout is changing for that, what will be the curvature? Okay, so when that Vout is changing here from 0 to VDD, let that output is changing from 0 to VDD. It is simply like when the Vout is 0, VDD minus 0 upon RD, that is maximum current is VDD upon RD. And when that Vout is VDD, so VDD minus VDD upon RD, that current is 0. And this is VDD minus Vout upon RD, that is negative slope like this. Yes, is it okay? So I am just explaining that okay, if you have a resistance and you have a Vout is changing from 0 to VDD, that graph is like this. Similarly, if you are putting this point, let I am thinking in such a way, okay, you have a drain current, this is drain current, and you have a Vout is changes. Vout is changing from 0 to VDD. What will happen? You know that ID versus VDS graph, where that VGS is fixed. Let that VGS is here and let that VGS is Vx, it will be like this. Okay, if the lambda is not 0. If lambda is 0, let the channel length modulation is not present, lambda is 0. Ideal case, it will be like this. Okay, so this is happening. If the Vout is changing from 0 to VDD and VGS is Vx, this is input is Vx voltage, it is providing like this. You can change that Vx voltage You can change that Vx voltage. If the Vx voltage is like this, if Vx voltage is, the gate voltage is less than that, so it will be like this and it will be like this. Yes or no? It depends on the gate voltage. This is Vx1, this is Vx2, this is Vx3. Okay. So if we are taking that both have a same, this is represented ID for Vout is changing and this ID for a MOSFET. If you are align both the MOSFET like this, if you are aligning both the MOSFET and resistance, let I am aligning this resistance, and if the MOSFET with the input voltage, and you have a RD and you have a Vout and you have VDD, now the graph is like this with respect of ID versus Vout. So the graph is like this. It can be like this. It can be like this. It can be like this. It depends on the different gate voltage. And similarly, that current will be, okay, just I am designing such a way, okay, that current, this is like this. Okay, that at a VDD it will be 0 and the maximum current is VDD upon RD. So what is happening basically, if we are using that, this is Vx1, this is Vx2 and this is Vx3, okay, that MOSFET in, if you are talking about Vx3, the MOSFET in that, this is the point where they are crossing to each other, that MOSFET enter in a linear region. If you are putting that this RD and you are putting the gate voltage Vx3, for that the MOSFET in linear region, MOSFET enter in a linear region. Why? Because Vout is equal to VDD minus ID RD, and if you are using at Vin is equal to Vx3, you have a large amount of drain current, that Vout is less than VGS minus VTH, or I can say that Vx3 minus VTH. If you are using this region, that at this region the MOSFET in saturation, your MOSFET in saturation, and it is providing that it is changing. If you are taking that different W by L, it will be, if you are changing that Vx, a small amount of Vx is changes like this of the gate voltage and like this with a delta Vx changes of that. So it will be a current MOSFET enter in a saturation only. Maintain that saturation. Is it okay? So in such a way you are setting that MOSFET, the operating point in such a way you can choose Vx3, you can choose Vx2, you can choose Vx1, but we are thinking such a way कि okay, if you are using Vx2 or Vx3, that Vx3 if you are using, that MOSFET enter in a linear region. If I am changing that the delta Vx at here, so what will happen, this is like this and this is like this. So it is purely enter in a linear region. If you are changing the 10 millivolt on the extra, that MOSFET Vout is equal to VDD minus RD and the MOSFET enter in a linear region. I am just explaining that the gate voltage here. I am not focusing on the RD. RD also have an effect, But now I am just thinking that RD is fixed. Let RD is fixed here, and you are changing the gate voltage. So you can check it here if you are putting that Vx3, that MOSFET enter in a linear region. If you are putting that Vx2 and you are changing delta Vx, it maintains that saturation region. And at this region, that the output voltage is nearly about half. So it have a large amount of changes here. It have a range of that Vout can be changed. A large amount of change can be happen. If we are putting that region, it is nearly about VDD. It will be high towards VDD. But we want that you have a swing of large amount of that output is swinging properly. It is swinging properly, not to make that VDD and fix it, not to make it ground. It is mid of that, so it will be maintain the saturation region and it is making the good swing of that amplifier. So that's why we are not choosing Vx1, because if you are choosing the gate voltage is small, so you are finding that Vout is nearly about VDD, and it is let provide the output like this, it is fixed at VDD and it is providing that lower side. So for a VDD side, it is not swinging properly. Okay, so it may be a problem. So that is the way you can understand. Similarly, what will happen when you are changing that RD? If you are changing the RD, let I am increasing the RD. And if you are increasing the RD, the output current is VDD minus Vout upon RD, that Vout is 0, so VDD minus 0 upon RD, that point, let this is VDD upon RD1, where RD1 is greater than RD. And due to this, you have this point, this load line, that is called DC load line. Okay. Now, for Vx3 is perfectly linear, for Vx2 is also in linear. For Vx only it is saturation. So you cannot increase the RD also. If you are designing a common source amplifier, you cannot increase RD also, because RD will be increase your gain. We will discuss the small signal model and you will find that RD will help you to increase your gain. But we cannot increase RD as much. If you are increasing your RD, for that RD, that Vx2 is perfectly in saturation region. For this gate voltage, if you are changing a delta Vx, the MOSFET is maintained in saturation region. But if you are putting that higher RD, let RD is here, and if you are putting that RD1 for making that higher gain, so what is happening? The load line will be shifted downwards. That it is not VDD by RD, it is VDD by RD1. That current is reduces. And it is like this, because the current at 0 at VDD only, because VDD minus VDD upon RD, that current is 0. But VDD minus 0 upon RD1 will provide the less current. And due to this load line, Vx3 is perfectly linear, Vx2 is also in linear, Vx1 only in saturation region. So if you are finding that operating point, you must be very clear. Okay, if you are changing that RD for making that higher gain, so it will be make that MOSFET enter in a linear region. Okay, so that is the major problem in a setting that operating point. Okay, so that input, you are setting that input in such a way that the MOSFET is maintained in saturation region if you are changing out delta Vx. And it should be in such a range that Vout will be near to center of that. Because if it is near to VDD or near to ground, it will not provide a full swing. It is like this, or it can be like this. Yes or no? Okay. So we are thinking that Vout should be in such a way that you have a full swing of that output also. Okay. let's talk about that. We are assuming okay, you have a resistance and you have a MOSFET and you have a this and you have a RD, you have a VDD and you have a VSS and you have a VGS, and you talk about ID versus VDS or Vout. So you find that okay, let I am putting that Vx2. So this is Vx2. For Vx2 this is like this, okay, and this will provide a load line, that is VDD upon RD, and this is VDD, this is 0, okay. And if we are changing that W by L of the parameter, you can change the gate voltage, you can change the resistance, you can change the parameter of the MOSFET, that is W by L also. So till now we are changing the gate voltage, we are changing the resistance voltage. Now I am talking about if we are changing the W by L of the MOSFET. So what will happen? Let this is the current, that ID versus VDS for W by L. Let I am increasing the W by L of 1 and W by L of 2. So if we are increasing W by L, so current will be increases. So this is W by L of 2. That current will be increases. Similarly, if we are reduces W by L of 0 for Vx2, the current is decreases. The current is depends on the W by L. You know that ID is half mu n CoX W by L VGS minus VTH ka whole square when the MOSFET in saturation region. So basically current is increases when the W by L increases. So if we are putting that, and if you want a high amount of current at the drain side, if you are increases, you are fit that let the operating voltage is Vx, but I want to and your RD is also fixed, your gate voltage is fixed, your RD is fixed, your VDD is fixed, your source voltage is grounded, and now you are changing the width and length or the ratio of W by L, and you are increases or decreases. So what will happen? If you are increasing the W by L, so basically current will increases, and if the current is increases, so V out is equal to VDD minus ID RD, and as per the current will increases, your V out is decreases, and if V out is less than VGS minus VTS, the MOSFET enter in a linear region. So if you are looking at here, this point at which the MOSFET in saturation, but at this point the MOSFET in linear. This is the point where the MOSFET in linear, that is the point that the MOSFET in saturation. So you cannot increase W by L higher for making it a higher current, because that current will be higher, your transconductance will be higher. That current is directly proportional to transconductance. Gm is equal to dou ID by dou VGS. If the current is higher, so your transconductance will higher, and transconductance will higher, so the gain will be higher. So for increasing your gain, you can be increase the W by L. But focus at here, if you are increasing the W by L of the MOSFET may enter in a linear region there. So for increasing the gain, you must have a limitation here. You cannot increase that much as you want. You have a limitation. If you increase that current by the help of W by L, you will find that the MOSFET may enter in a linear region. If you increase that RD for the making that higher gain, it will be make the MOSFET in a linear region, because VDD upon RD1 will be shifted here and it will be go into a linear region. Because the gain will be minus GMRD parallel or not, we will discuss in a small signal model, but these parameters will help you for a DC analysis. These all are the DC analysis. This is not transient analysis, this is not AC analysis. This is only a DC analysis. I am just changing that output from 0 to VDD. We know that Vout can be increased from 0 to VDD. And if that output is changing from 0 to VDD and you are changing the W by L of the MOSFET, that it may shift the MOSFET from saturation to linear. Okay, so just focus at here. Okay, you are trying to increase the gain, but your gain is not increases. The gain is decreases. If the gain is decreases, please check if you are increasing the W by L, the MOSFET enter in a linear or saturation. It is remain in saturation or shifted towards linear side. Okay, so these all are the parameters is DC analysis. I am just talking about the DC analysis. Firstly, you set the DC operating point with the help of fixed W by L, with the fixed RD and VDD. You will twin that RD, you will twin that W by L, where you will find that maximum swing with the variation of Vx, or you are finding that the good voltage of that Vx of the gate where the MOSFET in saturation, and if you are changing that gate voltage, you will find the large transconductance also of that, and you will find the large current also. Okay, you can analysis of the DC. Here I am just explaining that ID versus VDS or ID versus VGS. You can provide that cadence as a command. You can give that command to the cadence. It will provide every plot. ID versus VGS, ID versus VGS, GM versus VGS, and CGS versus VGS. Every parameter, as you have a DC. In a DC, the MOSFET have a lot of parameter. But if you provide that, okay, I want everything with respect of VGS, it will provide everything in terms of plot. And you can check it. This value of the gate voltage is very good, where that you will find that large transconductance, large current, and large output voltage. And similarly, you have a large RD also. Okay, so you can. That's why tool is important. Firstly, you analyze what is happening with the help of variation of W by L, with the variation of VGS, with the variation of RD. Everything you know, then you go for the tool and set your parameter, and you can find it. Okay. So after set the operating point, you know that you have a MOSFET here and you have a gate voltage, and you are trying to find out output voltage. Let I am providing that Vx as a gate voltage, that is DC voltage, and I am changing that delta Vx at here, that is a small change it, and this is your RD. So as a change of the small signal model, you are talking about the small signal model, you make that 0 where that it have a fixed voltage. So this VDD is your fixed voltage, so it become a 0, that is grounded. This Vx is your DC voltage, so the Vx become a 0 and delta Vx is present. So the circuit will be like this. Okay, you have a resistance, you have a MOSFET, and now you have a voltage is delta Vx, because delta Vx is changing. On the basis of that, your output is changing and your VDD is fixed, that's why it is 0, and now it's become a delta Vout, not a Vout, it's a delta Vout, a small change of that. So this is a small signal. Okay, you can convert into a small signal model. So what is the small signal model? That small signal model is fixed for a MOSFET. Let I am using that R0, let lambda is not 0. Channel length modulation is present, let lambda is not 0. If lambda is 0, so R0 will be infinite, it will be act like an open circuit. Okay, so here you have a gate, you have a drain, and you have a source, and source is grounded. So I make that source is grounded. You have a gate voltage that is Vx, delta Vx. So I am providing the delta Vx at here. This is your GM VGS. So GM and VGS, and at source is grounded. At the drain side, you are talking about delta V out, and the with V out you have a RD. So you have a RD with ground, and here you are talking about delta V out. So this is your small signal model. Okay. So what is happening basically? GM VGS, what that gate and source voltage at VGS is what? That is delta Vx minus 0, it will be delta Vx. So this is GM delta Vx, and R naught is grounded drain terminal. This is drain terminal, this is grounded, this is drain terminal, this is grounded. So basically R naught and RD are in parallel, and current is entering from the bottom to top. So it's not positive, it is negative, because the current is entering from the top, so it is V out is positive. Here that current is increasing from bottom to top, from ground to towards that V out. So V out is what? The delta V out is your is minus GM delta Vx RD parallel of R naught. Here is a phase difference in a common source amplifier. The phase difference is 180 degree. Why? Because the input is delta Vx positive and your output is negative. That have a phase difference of 180 degree. Okay, and delta V out is minus GM delta Vx RD parallel of R naught, and you can say that the gain is what? That gain, or you can say that delta V out upon delta Vx will be minus GM RD parallel of R naught. Okay, so this is the pure gain of the common source amplifier. This is only possible when that MOSFET in saturation region, and if the MOSFET in saturation region and you are changing the delta Vx, the MOSFET maintain that saturation region, then only minus GM RD parallel of R naught is possible. And by this you can think that that gain is minus GM RD parallel of R naught. So how can you increase your gain? So you can increase your gain by the increases of the transconductance, that is GM, or you can increase your RD parallel of R naught. So it can be possible by the increment of the transconductance or by the increment of the RD and R naught. Okay. So as you know that if you are increasing your transconductance, if you are increasing the transconductance by the help of W by L or by the help of VGS, that MOSFET may enter in a linear region. Okay, so if you are increasing your transconductance, your drain current should be increases. Your drain current is increased, then only the transconductance will increases. But focus at here, if drain current is increases, so V out is VDD minus ID RD there. So MOSFET may enter in a linear region. Okay, it may be VGS less than VGS minus VT. Second thing, you can increase your RD. If you increase your RD, it is also will affect your MOSFET. So the MOSFET may enter in a linear region because V out is equal to VDD minus ID RD. And if RD is increases, MOSFET may enter in a linear region. So you have a thinking of that, ki, okay, if you are increasing RD, what will happen? If you are increasing R naught, what will happen? If you are increasing GM, what will happen? So always think in such a way ki your MOSFET must enter in a saturation region. It will maintain in a saturation region. It will not pass towards linear or cutoff. Okay. And if you talk about, let RD is very high as compared to R naught, that gain will be minus GM-R naught. That is called intrinsic gain. That is called intrinsic gain of the MOSFET. This is the intrinsic gain minus GM-R naught. If RD is very large as compared to R naught, if RD is very large as compared to R naught, what is that meaning? If RD is very large than R naught, that the meaning that you are using that load resistance in such a way that load resistance is very high. Then only that this will provide the transconductance is the gain will be minus GM-R naught. Okay. So of course you have a lot of things. You have a W by L, you have a VGS, and you have a RD. Lot of things at here you can change and you can find that gain. But if you have a project, always that you have a design specification. Okay, design a common source amplifier where that gain is 20 dB. So if you know that 20 dB gain means GM-RD parallel of R naught, I can say that okay, that gain is 20 dB. Okay, so that means GM-RD parallel of R naught is 20 dB. Yes, hello. Yes, everyone. Is it? So you know gain. So 20 log of GM-RD parallel of R naught is equal to 20 dB. So you can determine such a way and you can pass it. Okay, what can you do so that it will be basically become a 20 dB. Okay, so you will check that what will be the GM, what will be RD and parallel of R naught. You have a must understanding. Okay, so it is given that that gain is 20 dB. Power dissipation is that is power dissipation is 10 microwatt. Okay, that maximum power supply VDD is 1 volt for a GPDK 45. So if power dissipation is 10 microwatt and you have a 100 microwatt or 10 microwatt, okay, and you have a 1 volt and 10 micro, and sorry, that you don't know about that ID, so you can say that ID is equal to what? That ID is equal to 10 microwatt upon 1 volt, that will be 10 micro. Yes or no? So that is the way you can determine is what is the current you have. If you know the current, you can determine the transconductance, because we have a different formula of the transconductance. We have a 3 formula of the transconductance. That what is that 3 formula? That GM is equal to mu n COX W by L VGS minus VTH. GM is equal to 2ID upon VGS minus VTH. GM is equal to under root 2 mu n COX W by L ID. You can check it. That is ID is equal to half mu n COX W by L VGS minus VTH ka whole square. That will be equal to that. 2 ID upon VGS minus VTH is equal to GMU. So every formula will have a 2 parameter variation, that is W by L or VGS minus VTH. Here you have ID or VGS minus VTH. You have a W by L or ID. As per that parameter variation you have, you can use your formula. It can be used like this, it can be used like this, it can be like this. You have a one of that is fixed and one of that will be vary. You can determine the transconductance. Okay. So GM is affected with ID also and VGS minus VT. In this formula, you will find that Gm is directly proportional to VGS minus VTS. Here you will find that Gm is inversely proportional to VGS minus VTS. But it is okay because that 2ID that will be providing that VGS minus VTS ka whole square. Okay. So you will set that Gm as per the requirement and you can find it. Okay. So this is the way you can determine that common source amplifier, and that we know that the intrinsic gain is minus Gm R naught when Rd is infinite. That means I am just explaining in such a way that you are using a current source where that ideal current source, in an ideal current source that the resistance is infinite, the internal resistance of current is infinite. So are using at ideal current source and you have a VGS at here, that is input voltage, and you are talking about the V out. Now you can check it. You can check it. This is minus G. The gain is minus GM RD parallel of R naught, where that RD is infinite because the drain resistance is infinite. Ideally, this is diode is that the current source is that is infinite. So you can use a current source if you know that current source, if you know the current mirror, so you can use it, or you can use a current source where that you have a drain resistance or that is infinite, so that for this MOSFET you will find that gain is minus Gm R naught there. This is one line question. Okay, so this is minus Gm R naught. Okay, so this is the way you can work on it. Now we are going for second method. How can you make a common source amplifier with a active load? Okay, with a PMOS. Okay, and we will discuss about the input impedance, output impedance. How can we use that common drain? And this is also a common source amplifier is what? Basically, this is voltage controlled current source amplifier. That you are providing that gate voltage, that is voltage control, and you're finding the output current. Basically what is happening in a small signal model, you can check it. Okay, you are changing that a gate voltage and you are finding that drain current, that dependency on the GM VGS. This is voltage controlled current source. Okay, that common source amplifier you will use every type of that. You will use a differential amplifier or current mirror or OTA, or everywhere you will use the common source amplifier for amplification. This is very good for amplification. Okay, and this is also provide, it is just like a common emitter in a BJT. That common emitter is also work like, okay, that it have a 180-degree phase difference. This common source amplifier is also behave like 180-degree phase difference. Okay, so we will check that what is the input impedance, what is the output impedance in the next class, and then we will talk about that active load. Till now we are talking about the resistive load and current load, and now we are going for diode based load and active load, and then we talk about common drain and common gate. With the resistive load, we find that the load line is fixed, that it is provided as a straight line. So it is not providing a good saturation region. So how can we increase that saturation region with a load? We can replace RD and we will put something and we will find that a higher good saturation region. Okay, where that NMOS will be in saturation region, maintain that saturation region. For this RD, it is not good for a saturation region. You have a change, a small change of RD, it will change that MOSFET may enter in a linear region. Okay, so we will talk about that in the next class. So till now, thank you so much everyone. Please work on that, the common source amplifier, and design that common source amplifier at 20 dB or 30 dB gain, and find that what is RD, what is R naught, and something like that. Okay, thank you so much everyone. Bye bye, take care.